Okay, today's meeting is going to focus on uses of the definite integral. And two uses in particular that we're going to cover are using a definite integral to determine the volume of a solid of revolution. I know that sounds really weird, but I'll explain it a little more in detail. This isn't going to be super useful to you as a business major, but it's one of the classic uses of a definite integral, and I'd feel like I'd left something out if I didn't describe it to you. Besides, I have an app that I want to show you that's really cool that will actually generate a solid, and you can see exactly what it is that we're talking about. The more useful thing from a business point of view is using the definite integral to find the average value of a function. So maybe you want to find an average stock price over a number of quarters, or an average cost of a particular item over the time that you're selling it, things like that. Okay, so I'm going to use my notes as a guide. Okay, so we'll start with that. I'm also going to be bringing up the TI-84 because I want to show you an interesting feature on your TI-84 you might not have realized was there. And I'll also, like I said, bring up this other app for solids of revolution. We'll bring up Word documents. And in any event, I'll share all of this with you when I upload the video for this session. So let me share my desktop. And we'll start with my notes. Okay, so as I'm saying here, I'm kind of putting in the disclaimer. I'm not going to spend a lot of time on volume because, again, that is the reason why you might want to know the volume of a solid of revolution is mainly in an engineering context. If you have a part and you've used something called computer-aided design or CAD to create the part, you might have a function that describes the shape of the part. And again, it may be something you're 3D printing or whatever, and you need to know the volume of it because you have to pack it, or you need to know the weight of it, or you need to paint it, or all sorts of things. You might need to know its volume. But again, those are from engineering contexts. Another reason you might need to know the volume of a solid is it might be difficult to actually go out and measure the volume. For example, suppose you needed to know the volume of an asteroid, okay? If you have a function that describes it, let's say it's basically the shape of an ellipsoid, like an egg-shaped thing, you could calculate the volume of it using this method. Okay, so again, it's primarily used in engineering contexts, and especially when it's difficult to measure volume directly. Okay, so again, that disclaimer said the topic will not be on your final exam, but there is some homework on it just so you can practice with it. Okay, again, it's one of the classic uses of a definite integral. So there are multiple methods for finding the volume of a solid of revolution. We're going to use something called the disk method, but let's not get ahead of ourselves. Let me first explain what I mean by a solid of revolution. Okay, so let's take a look at these two really crude drawings here. Suppose we have, let's look on the left, suppose we have a function f of x equals x plus 1. Okay, and let's say for the purposes of our discussion, it is always above the x-axis. It's always positive, it's non-negative. And you are interested in the graph of this function between two x values. So here I've picked x equals 1 and x equals 4, and you can see those as vertical lines in my drawing here. So you know that this function and these two vertical lines and the x-axis create this purple region, okay? So the region is bounded by those lines, okay? And I deliberately picked something very simple so you could see it. Now, suppose we take this function line f of x and we revolve it or we rotate it around the x-axis to create a solid. Now, again, this is a really crude drawing over here. What I want you to pay attention to is this purple thing inside. That's my original region that you're seeing over here. But if I rotate it, what you're going to get is kind of like part of a cone. Okay, it's going to have a round base. Okay, and you can imagine slicing it into discs like this. Okay, so again, this is my crude drawing. What I want to share with you is a different app. Okay, and I believe the app is called Shodor.org. I'm going to see if I can switch to it without trashing anything else. I think I already have it open. I just need to find it in my toolbar. So, let's see. Oops. Okay, so here it is. Okay, it's Shodor.org. Okay, so again, let me see if I can bring that. I'm typing it in the chat so you can see it, Shodor.org. I also have this in our notes. Okay, so basically, if you go into our My Math Lab course, you go into the section on chapter 16, you'll see this under applets. Okay, so what I've done already, if you want to kind of see what I've got here, right, it gives you some boxes. It says functions, right? So I'm putting in the function I'm interested in. Okay, that was the top of that purple region, f of x equals x plus 1. Okay, and notice it says leave g of x blank for the disk method. So we're using this disk method, so I'm going to leave that alone. And then I'm interested in it from 1 to 4. You can see that over here. Okay, they've just graphed it from 1 to 4 on the axis. Okay, so you're only seeing part of that line. Okay, and then over here it says revolve. And again, it'll do it medium, fast, or slow. So I'm going to say let's do it slowly so we can see it. All right, and I want to revolve it across y equals 0, which is the x-axis. Okay, so let me stop over here and ask you, everybody understand the setup? Okay, setup clear. Again, I'm trying to show you a better drawing of what I had in my notes, because again, I am not an artist. Okay, so again, this will actually show you the solid and it will calculate volume for you. Now, what's the use of this? Okay, well, you're going to use it to check what you do manually, because again, you're expected to be able to do this with calculus. Okay, and I'll show you the formula for doing it in a minute. Okay, but I want to show you this as a check, as well as so you have a visual representation of what it is you're trying to find. Okay, so now I'm going to hit the revolve button, and you should see it revolve slowly around the x-axis. Okay, see it's going around. And again, it's difficult, that leading red line is the function. Okay, and so then what I can do is I can turn this slightly and you can see what it created. Okay, so basically, you can see what I've got is part of a cone. And when I talk about volume, I'm talking about the empty space inside. Okay, so it gives you the volume of this shape is 122.521 cubic units. And the surface area of it, okay, that's the outside shape, that's 93.301 square units. Okay, so again, I'm going to just stop and pause. Is this okay? Okay, do you understand what it did? Okay, and it's creating the shape I'm trying to draw in my notes, but this is a much better rendition of it. Okay, is this okay? So again, if you want to use this app, you're going to put your function here, your x limits down here, okay, and then you're just going to make sure you have across y equals 0, because that's the x-axis, right? And then you can use this as a check for any work that you do for any of these problems. So again, let me go back to my notes and we can bop in between these options that we have. Okay, so you can see that, again, just trying to get stuff out of the way. So, all right, so you can imagine then what I've got here, this volume I'm interested in finding, I can slice into these disks, okay? And what you want to kind of realize you've got here is the radius of each disk, okay, from the x-axis up to the disk is given by, well, your function value, okay? And basically then the width of the disk, you can kind of think of as this area, this length on your x-axis that can be of arbitrary size, right? We've been calling it dx, okay? And we can let dx get smaller and smaller and smaller, okay? So if you remember the formula for the area, I guess an area of a circle, right? That's the radius squared, pi r squared, right? And then you want to basically take this circular base and multiply by the thickness, okay? But the thickness is going to be getting smaller and smaller and smaller. So take a look at what I've got down here. I have pi times the radius, which is f of x squared, times delta x, which is these chunks along the x-axis, right? And I'm going to take the sum from I equals 1 to n of all of those chunks or disks. But because this is a calculus class, okay, what we want to do is we want to approximate this by a definite integral. So in order to do that, I need to take the limit of the sum, okay, as delta x gets really, really small as it approaches 0, okay? And you can see what happens then. This morphs into a definite integral, okay, from a to b, okay, which is from my example from 1 to 4, of pi times the function squared, and the delta x turns into dx, okay? So again, I'm really glossing over where this is coming from because I know, again, in this class, we don't need to focus on proofs of anything, but I just kind of want to give you an idea of what I'm doing. I'm slicing this volume into tiny little disks, okay? And they're going to be cylinders, right? So I'm trying to find the volume of each of those little cylindrical disks, okay? They have a circular base, okay, because I did a revolve, okay? And so that's why you're seeing something that looks like the area of a circle in this formula. So I guess I'm just going to ask, do you follow? Okay, you don't have to worry about having to recreate the description or anything, but is it clear? Do you follow what I'm showing you? All we're going to be using is this formula down here with the integral, okay? Right. Anybody questions at this point? So all of the discussion here has resulted in this formula for finding the volume of a solid that's bounded by the function f of x, which is going to be always above your x-axis, okay, from x equals a to x equals b, if you rotate the thing around the x-axis, okay? So let's do it with my function, okay? It's breaking the solid into disks, so this is called the disk method, as opposed to other methods called the washer method, okay, or the shell method. Don't worry about those, okay? So again, I'm explaining where all these pieces are coming from, but I've already done that, so I'm not going to do it again. So again, if you wanted to find the volume of a cylinder, you take the area of its circular base, and then you multiply it by its height, and the height is the dx part. Okay, so let's try it with our formula, okay? So our f of x was x plus 1, so I'm putting that in here for f of x. Here's the pi that's part of the formula, and I'm putting a equals 1 and b equals 4 in my integral bounds, okay? Now, again, pi is a constant, so you can just pull it through the integral, okay? And what I'm doing here with the x plus 1 squared, just to make it easier, is I could leave it like this and treat it like a lump like u, okay? But rather than do that, I'm going to square it. Okay, so everybody remember how to square a binomial? Okay, you square the first term, that's x squared. You square the last term, it's always going to be positive, so there's the plus 1. You multiply these two together, so x times positive 1 is positive x, and then you double it. Okay, so that gives you the term in the middle. Okay, so everybody okay with squaring a binomial? Okay, I want to make sure you understand where this x squared plus 2x plus 1 came from. Okay, is that okay with people? Good, good, good. All right. Okay, so let us move on down. Then it becomes an integral problem. It's just a definite integral. Okay, so I'm going to integrate here. Okay, I can use the power rule on all of these. Okay, so again, to integrate x squared, I'm going to add 1 to the exponent, get x cubed, put that over the new exponent. So that gives me x cubed over 3. Integrate 2x to the first, okay? Add 1 to the exponent, that gives me x squared over 2. The 2 outside and the 2 underneath cancel, and I just get x squared. Okay, and then this is 1 times x to the 0, right? Because again, x to the 0 is just 1. So I'm going to add 1 to my exponent. That'll give me x to the first, okay? And then put that over 1, so that gives me x, okay? So anybody questions on the integration part? Is everybody all right with this integration? I want to make sure we're following. Okay, I'm not hearing any questions. We're good. All right, so this is not anything new. The only thing new was using the formula up here. Okay. So because it's a definite integral, notice I'm pulling the pi outside of everything. Okay. So the way you have to evaluate it is you have to use the fundamental theorem of calculus. You've got to put in your upper bound first. So here's the 4 going in, okay, to all of these terms. Then you subtract, okay, the lower bound, evaluating in all of those terms. And please, the important thing to note here is this second expression is in parentheses because you want to make sure this minus sign distributes to everything beyond, okay? So over here, you're going to have 4 cubed, right, which is going to be, I think, 64 thirds plus 16 plus 4 minus 1/3 plus 1 plus another 1. That whole mess, okay, turns into 39 pi cubic units, okay? So again, if you were doing this problem, say in my math lab, and my math lab asks you for an exact volume, this is what you would need to type in. Okay, because if you approximate pi, you're not going to get an exact answer. I guess the point I'm making is you can use the technology to kind of give you an idea as to whether you're doing the problem correctly, but you're going to have to go through the calculus steps here and evaluate it to get an exact answer. Your calculator and these apps that I'm showing you online will not give you an exact answer. Okay? So hopefully that's clear to everybody. Right? So this is an exact answer. Let's go take a look at some of the other technology. Okay, so I'm going to show you the app that we were at before, that Interactivate thing on Shodor. I'm going to go back to that. Okay, this is giving me a volume of 122.521. Okay, so if you wanted to check to see that this is equivalent to 39 pi, what you'd need to do is you'd need to take your calculator and you'd need to type in 39 pi. Okay, and you'd have to see if that's approximately 122.521. And it is, there's a rounding error, okay? But you can check it that way, okay? You can say, hey, 39 pi is about this number, so I guess I'm doing it correctly, okay? So you're welcome to use the app to check. I also want to show you something on your TI-84 that you might not be familiar with. So I'm going to bring up my TI-84 emulator here. Okay, so what I've got over here is the plain old TI-84 CE. Okay, and I want to show you something on the math menu. Okay, everybody see number 9 down here? Number 9 says function integral. Okay, and that basically is a definite integral. So again, it will do the same thing. It will numerically approximate a definite integral. Your calculator isn't doing calculus. It's using a numerical approximation. So again, your answer's off a little. Okay, so let me select this. Again, I got this from Maths. I'm just in the Maths menu, and I'm going to pick number 9. I'll show you what it does. It brings up a template for you to enter in stuff. Okay, so I'm going to enter in the formula that we just evaluated. Okay, so that was the integral from 1 to 4. And then the formula we used was pi times the square of our function. Okay, so here's pi. And then I'm going to need parentheses because I'm going to square the thing. Okay, so I'm going to put in my function. That was x plus 1. Close the parentheses. And then I want to square that whole function. So x squared, right? And then I'm going to go out here, and they want to know what are you integrating with respect to? So I'm going to put the x there again. Okay. So let me stop and ask, is everybody okay with what I did? Okay. Anybody questions? Okay. Again, I'm just copying the formula from the notes. Okay. I'm showing you multiple ways you can check your answer. All right, so again, this is for the solid of revolution. And then all you have to do is hit enter. Enter on the calculator, and you get 122.522. That's the same thing that came out of the solid of revolution app. And if you want to double check, we got this exact answer, 39 pi. You can see that gives you the same value. So again, I'm showing you how to do solids of revolution in the app at showdoor.org. I'm showing you how to use it with FNInt on your calculator. So again, these are ways you can check your work, okay? But like I mentioned, my math lab's going to want an exact answer. So of course, it's going to expect you to actually work it out in steps, like in my notes. All right? Anybody have any questions at this point? I'd like us to try one. Okay, so if you guys don't have any questions on how we did any of this, I'm going to move over to a Word document. Okay, and I'm showing you, here's a volume of a solid formula. If f of x is non-negative, that means it doesn't dip below the x-axis, and r is the region between that function and the x-axis, from x equals a to x equals b, then the volume of the solid formed by rotating it about the x-axis is given by this. So here's the one I'd like you to try. You try this one. Find the volume of a solid created by rotating the region that's bounded by f of x equals x squared plus 1, x equals -1, and x equals 1 and the y and the x-axis. Okay, so you try this one. Okay, so try using the formula. Okay, and I'll attempt to be working it here. Okay, feel free to graph it with Shodor, graph it with function int, do whatever it is you need to do, okay, to check your work, but you need to be able to walk through the calculus steps too. Again, I can tell if you've got questions, so just type them in the chat if you're lost with what we're doing, okay? But I need you to try this. How are we doing? Is anybody stuck? Okay, folks, again, I can't really see if you're struggling or not. I'm kind of depending on you to let me know if you're stuck anywhere. So I realize you're all probably still working on this. But let's take a look at what I have here on the screen. Okay, and please feel free to ask questions if any of the steps make no sense. Okay, so here's what was our statement. Okay, and again, I used the formula for a solid of revolution around the x-axis between my function and the x-axis, bounded by two vertical lines. Okay, so what you have to be able to do is translate this into the right plugins here. Of course, f of x is easy. Okay, I'm going to put in x squared plus 1 for that. Pi is a constant. It comes along for the ride. Okay, but then you have to realize the x values are your lower and your upper bounds on your integral. Okay, so hopefully everybody is all right with the way I plugged this in. Okay, so here's the formula, and here it is with my values plugged into it. Okay. So as far as trying to integrate it by hand, I'm going to pull through the constant pi. Okay, that can just sit outside until the end. And then I am going to expand this binomial, right? So basically, I'm going to square the first term. So x squared squared is x to the fourth. Square the last term, that's a plus 1. Multiply these two together, that's positive 1x squared, and then double it, positive 2x squared. Okay? So that's how you square a binomial. Just so you know, okay, there are calculators online that will square polynomials for you. Okay, so if you're struggling with stuff like that, please take a look online, or you can even ask me, hey, I remember you said there was a way to, find an app to square this. I can show you where those are. Again, I'm assuming you know algebra, but don't let the algebra become a roadblock to understanding the calculus, okay? So here's the expanded binomial, and that just makes it easier to actually integrate. Okay, so integrating term by term, this gives me x to the 5th over 5. This part, I'm going to just pull the 2 away for a minute, and this one will give me x cubed over 3 times 2, so 2/3 x cubed. And then, of course, the 1 just gives me an x. All right, so hopefully everybody is all right with the integration. If you've got any questions, just type them in the chat. Then we're evaluating it from the lower bound to the upper bound. So here's the upper bound first. Notice how I pulled pi out of everything. Okay, and that's just going to multiply the final number that comes out of this. So here's upper bound, the 1 going in. Here's the lower bound going in. And I used my calculator to evaluate this. And I also asked the calculator to give it to me as a fraction, because that's probably what my math lab's going to want, an exact value. Okay, so just remember, decimals tend to be approximations unless the decimals terminate or repeat. Okay, so fractions are exact. Also, pi, the symbol, is exact, whereas 3.1417 is an approximation. So again, you have to be aware of these things when you're trying to find exact values. So the numerical part here gives me 56/15 times pi, and that's approximately 11.729. Okay. So let me ask, are you okay with the steps? Okay with these steps? Can you please do me a favor and just shout out in the chat either a yes or a no, I'm following you, or no, I'm stuck on this step. Please take a minute and give me a shout out. Okay, we got one yes. How about the rest of you? Are any of you stuck on the steps? Now is the time to ask. Questions, people. I would actually, there's a bunch of you on, and some of you aren't letting me know where you are, so I'm kind of not willing to move on just yet until I hear from more of you. How we doing? Okay, at this point, I guess I'm just asking you, do the steps that are on the screen make sense to you? I'm not necessarily asking, can you generate them? I'm hoping you can, but I just want to make sure they're clear. Okay. Let's take a look at the two pieces of technology I showed you, and let's see how those approximate. Okay, again, you kind of want to keep track of these values here. You've got an exact value here, okay, and an approximate value here. Okay, so you just want to kind of keep those in mind, especially the approximate value. And let's take a look at that app I showed you at showdoor.org. Okay, what I'm going to do is I'm going to clear this function. Okay, let's see, clear graph. Okay, and then put in this function that I had, okay, which was x squared plus 1. And my bounds were from -1, +1. And then I'm going to say set function. Okay, and you can see here's the graph of that function, okay, between -1 and +1. I still want to revolve across y equals 0, and I'm going to do it slowly so you can see it. And there it is. You're seeing something being created, and I'm going to let it generate the whole thing nice and slow. And then when it's done, I'll tilt the grid a little so you can see what it looks like. Okay, so here's tilting the grid just a bit. See the solid. So this kind of looks like a ring, but a ring with a channel in the middle of it. You know, kind of like something a pulley might have in it, where the rope goes around like this. And again, you can see our volume over here is 11.729, which is an approximation of the value that we got. Okay, so again, you can see how to use this tool to check your work. Okay, I'm going to go back. Is everybody all right with this one? Okay, now again, this tool exists on the internet, so if you can log on, okay, again, it's at showdoor.org. Again, I have a link to it in the apps section, the videos and notes, and it's under applets. So again, I like this tool because again, you get the picture, the 3D picture, which I think is cool. Okay. So let's do it with the TI then. Okay, I'm going to clear my screen here, clear this down here. All right, and remember how you do integration. If you want to actually build an integral from scratch, you can go into math all the way down to fn int, which is number 9. Okay, and again, the formula for doing solids of revolution, I have to remember that in order to use this. So I'm going to put in my lower bound, which was -1, put in my upper bound, which was +1. The formula said it's pi times the function squared, so I'm going to type that in again. Here's pi. I'm putting parentheses around the function because I have to square the whole thing. The function was x squared plus 1. Close the parentheses, square the whole function, right? So again, this is like the circular base of my cylinders, my discs, okay? And the dx is like the height of them, so make sure you put your x over here. So these are the area, the volumes of all the little cylinders I'm stacking up, and I'm just going to hit enter, and I get the same approximation. So again, are you okay with this tool as a check? Okay, with the TI as a check. I want to make sure you can use both of those technology methods to check your work. All right with this? But again, you can see these give you approximate answers. Even though they're out to 8 decimal places, they're still approximations. And 56/15 pi is an exact answer. Just want to make sure everybody's okay with that. So again, any questions on solids of revolution? Any questions on solids? We're not taking a deep dive into this by any means. Most calculus classes really pound on this topic, but we don't need to, okay? Again, I just wanted to show you how it's done and then show you some tools for checking your work. All right. So then the second topic we're going to cover today is average value. Okay, so let me go down there. The average value of a function. This is far more useful for you in terms of a business context, okay? So let's say we have n numbers, okay, and we want to average them, okay? So I'm calling them V1, V2, V3, right? Remember, what I call them doesn't really matter. The little subscripts, 1, 2, 3, all the way out to n are just labels. They're telling you this is the first number, that's the second number, this is the nth number. So here's adding them all up, and I'm dividing by how many there are. Okay. So another way to express this is the sum as I goes from 1 to n of v sub I. Okay, this is just summation notation, and it's telling you this thing is going to generate a sum of these v things. Okay, and I is going to keep track of the subscripts. So I is going to move from 1 all the way to n. So you're going to have v sub 1 plus v sub 2 plus v sub 3 all the way out to v sub n divided by n. Okay, so that's how you find a numeric average, right? It's the same thing we call a mean. But suppose you want to find the average value of some function on an interval a, b, a closed interval. Okay, we're going to do this in a similar way. What we're going to do is we're going to take the interval and divide it into sub-intervals that have that same width that you've seen over and over again in this class, delta x. Okay, and what's delta x? Delta x is a really small interval in x. Okay, then we're going to choose an x value, x sub I, so that it's inside that delta x, and then find the y value, f of x sub I, that goes with it. Okay? So the average function value then on those n subintervals could be thought of as this. Remember, these are y values. You want the function value, right? So f of x sub 1 plus f of x sub 2. And again, these are y values in each of the subintervals. Okay, so we wind up with this expression. Again, the sum as I goes from 1 to n of all these f of x sub i's divided by how many there are. Okay, now this part might be a bit of a reach. Okay, think about what delta x is. Okay, delta x is the difference between the upper end of the interval and the lower end of the interval divided by n, right? It's kind of like what we were doing when we were trying to do Riemann sums, and we wanted to figure out how many rectangles could I make within this interval, okay? Well, let's say I have, I want to make 3, okay, I want to have 3 sub-intervals, right? And let's say b is 4 and a is 1, okay? So b minus a, that's 3, divided by 3 means delta x is 1 wide, okay? So basically it's the same idea here, okay? So what we're going to do is we're going to multiply this right-hand side by b minus a over b minus a. Why are we doing that? That's a fancy form of 1, okay? And I'm kind of doing that because this b minus a will cancel out, okay? So look at what I'm doing here, okay? So here I'm winding up with, I'm pulling out a 1 over b minus a. This b minus a goes inside over here, okay? Because b minus a over n is what I'm substituting for delta x. And so I'm left with this as a formula, okay? Don't worry too much about the b minus a trickery, okay? It's a device that you can use algebraically to get things into the form you want them in, okay? There's no law that says you can't multiply anything by 1, but then you get to choose what form 1 is in. And in this particular example, b minus a over b minus a works, okay? Because I want to kind of rewrite my delta x as b minus a over n. Okay? So here's what I'm winding up with. 1 over b minus a times this sum. But again, since we're in calculus land, what we want to do here is we don't want a sum, we want an integral. So we're going to take the limit as the number of the subintervals gets infinitely large, right? And delta x is shrinking, okay? So I get the integral from a to b of f of x dx, but I have to keep this 1 over b minus a out in front. This is a formula for average value, okay? And what I did was kind of quickly show you where it comes from. It's called a derivation. I don't do that very often in this class because, again, it's not technically necessary, okay? You're not going to be asked to reproduce it. But I don't know about you, but I find it a little bit more satisfying to know where the formula came from. Otherwise, it's just a random formula that I have to memorize, okay? So everybody follow the derivation. Okay. So basically what I'm asking you is not can you recreate it, but are you all right with where this came from? Okay. Again, what I did was I just averaged some y values across an interval from a to b. And then I made those subintervals I made a lot of them. Okay. So I'm getting a better and better approximation of the average. Okay. All right, so as long as we're good at this point, let's work through an example, okay? So here's an example, right? So this is what you want to remember. Again, it's a definite integral from a to b, but just remember you have this 1 over b minus a out front. Okay, that's the only thing to remember. Right, so let's take a look. A stock analyst is plotting the price per share of a certain common stock as a function of time, and finds it can be approximated by this function. So S of t is the value of the stock. Let's assume it's in dollars. Okay, and t is the time in years since the stock was purchased. Okay, and you can see we have an exponential function here. Find the average price of the stock over the first 6 years that it was held. Okay, so again, you could be a stock analyst, you could be somebody's portfolio manager, and they want to know, well, what's the average value of this stock? I know what the high and the low was, but on average, what was it worth? Okay, so we're going to use the average value formula. They're asking us over the first 6 years. So that means our lower bound is 0, the time we actually purchased the stock that year. And the upper bound B is 6. Our function, of course, is the model for the value of the stock. So here it is plugged into the average value formula. 1 over B minus A. So that 1/6 just sits outside, right? It's just a coefficient. It's not going to influence any of the calculus we're doing, okay? Then I have the integral of this exponential times dt. Okay, so let's talk about actually integrating. Okay, so the first term is a constant. So that's like 25 t to the 0. I'm going to add 1 to t, put it over 1. This is going to give me 25t. Okay, you have to remember how to integrate this. Just pull away the 5 for a minute. You're integrating e to the minus 0.01t. Okay, remember what you do is you take this k in the exponent. You can think of it as the derivative of the exponent. Put it on the bottom. So there's the k on the bottom. And then just repeat e to the minus 0.01t. Okay, this is the 5 that was your coefficient. Okay, so now you got 5 over negative 0.01 as the coefficient on this exponential. Okay, and we're going to evaluate that from 0 to 6. Everyone okay with the integrating? Everybody okay with the integrating? Okay. Again, it's been a while since you've integrated exponentials, I know, but you do have an integration sheet. Again, if you can't find it, it should be in videos and notes, probably either in the chapter 15 or chapter 16 materials. If you still can't find it, please email me and I'll send it to you. All right, well, it's a definite integral. So again, according to the fundamental theorem of calculus, we need to evaluate this at the upper bound. So here is, again, I'm skipping some steps here. 25 times 6 is 150, okay? This 5 over negative 0.01, this is negative 1/100th. This whole thing becomes negative 500, but it's a minus sign out front. So I have plus 500e to the 0.06, okay, because this becomes a 6, right? Everybody good with that part? Here's the upper bound. The lower bound says, well, subtract what this is evaluated at 0, okay? So again, I realize looking at this, I probably shouldn't have left out so many steps. Let's see if I can put these in a comment. Okay, so what do we have here? We have 25 times 6 minus plus 500 to the negative point. That's the upper bound. And then I have minus, okay, the lower bound 0. So I have 25 times 0, which is 0. And then I have plus 500 e to the, now it's going to be negative 0.01 times 0, which is going to be 0. Okay, everybody all right with that? All right. So if you take a look at what that gives you, okay, this part is the 150 plus, this part doesn't change. I'm just with 500 e to the 0.06t, 06, sorry. Again, I'm just trying to break down the algebra a little more. Okay, then I have minus 25 times 0 is 0. 500 e to the 0, e to the 0 is a 1. So this is going to be 500 times 1. Okay, so that's where the minus 500 comes from. Is that algebra okay? Okay, I want to make sure everybody's good with the algebra. Okay, could you just give me a shout out so I'm sure everybody's following? Once you've got this expression, okay, and again, don't lose the 1/6 on the outside. This is something you just put into your calculator to evaluate. Okay, the exponential is going to create lots of decimal places. So usually they're going to want you to round to a certain decimal place. Since this is the average value of a stock, it makes sense that you want to round to the nearest hundredth, dollar cents. So at least pull one more decimal place so you can do that kind of rounding. So this comes out to 20.147, which means my stock average value is about $20.15 a share. Okay. So is this example okay? Is this example okay? Anybody got questions on it? We okay with it? So again, once you get the answer, you want to be able to interpret the answer in the context of the problem. This was an average value of the stock that was held for 6 years. So maybe its high value was $49, maybe its low value was $15, but on average, the stock value was about $20.15. Okay, let's have you try one then. Okay, I'm going to go over here to my Word document. I'm going to slide down. And I have an average value problem for you to try. Okay, so here's one. Here's the average value definition, right? So 1 over b minus a times the integral from a to b of your function. So here's a problem for you to try. The DeMarco Pasta Company receives 600 cases of imported tomato sauce every 30 days. The number of cases of sauce in inventory T days after the shipment arrives can be modeled by this function. Okay? Need you to find the average daily inventory. Okay, so you try this one. Okay, and we can approximate it with our TI-84 or whatever, but set it up and I'll be working on it here while you're working on it. Okay? If you're stuck anywhere, please make comments. Okay, put something in the chat so I can figure out what you've got. Oops. How are we doing? Anybody stuck? Did you realize you needed to do some algebra before you integrated this function? Okay. Namely, the square root of 30 and the t are both underneath the square root sign, right? The 30 and the t. So the first thing you need to do is separate those. Okay, you want to pull out the square root of 30 and keep that as part of your coefficient on that term. And then rewrite square root of t as t to the 1/2. Okay, so you needed to do a little bit of algebra before you did calculus. Okay. If you're not sure what I'm talking about, you can see it up here on the screen. Okay, folks, in the interests of time, I realize you're all still working, but I need you to focus on what's on the screen here. Okay. So again, if I wanted to find average daily inventory, okay, basically here's the function that tells me, it models my inventory T days after the shipment arrives. And again, what you want to pay attention to in this function is that both the 30 and the t are under the radical sign. So the first thing I'm going to do is I'm going to separate those out. Why am I doing that? Because square root of 30 is just a number. Square root of t is a variable, and I need to do calculus on it. So you might remember, if you've got a product under a square root sign, you can separate it into a product of square roots, which is what I'm doing in this first line here. Okay, so now my coefficient on this term is 20 times the square root of 30, and I'm writing the square root of t as t to the 1/2. Okay, so that little bit of algebra makes the whole problem a lot easier to do. Now I'm going to plug this n of t into my average value formula. Okay, so I have 1 over b minus a. Again, what's what's the upper bound on my inventory? Well, it's the 30 days that's between the inventory shipment, the shipments that I get of tomato sauce. So my lower bound is 0. That means that's the day I got a shipment. And 30 is going to be the day before I get the next one. Okay, so I have 1 over b minus a. Those are the same bounds on the integral. Okay, And then over here, I have my function, which is written now as 600 minus 20 times the square root of 30 t to the 1/2 dt. Okay. Doing the integration, okay, again, I get 600t. This is just a coefficient, so I'm leaving it alone. I'm just paying attention to the t to the 1/2, and I'm integrating it with the power rule. So I'm taking 1/2 and I'm adding 1 to it to get 3/2. And then I'm putting that over the new exponent 3/2. Okay, so this is ugly right now, but don't worry about it. We'll fix it. Okay, pull the coefficient away and then just work on the variable parts. Then I want to evaluate this from 0 to 30. Again, the trick is don't lose this 1/30th out in front. It's real easy to just drop it off by mistake. So here's what I did. I said, well, t to the 3/2 is t to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So this 2 is going to come up in the numerator and multiply the 20. So 20 turns into 40. Okay, so now I have 40 square roots of 30. The 3 stays in the denominator, but I'm pulling it away. Okay, this is now my new coefficient. 40 square roots of 30 over 3. Okay, times t to the 3/2. Okay, take the time to do some algebra in between the calculus step, okay, because basically it makes your life easier. Then I'm going to use the fundamental theorem to evaluate this. You can see by looking at this, if I plug in a 0, this term goes away, and so does this term. Okay, 0 to any power is 0, so this term will go away too. That's what I have the -0 over here for. Okay, I'm just making a mental note. I don't need to evaluate at the lower bound. All of these terms will drop out. That's kind of a shortcut. So here it is evaluated at the upper bound. I have 600 times 30. Here's this weird coefficient. And then here's the 30 going in for t. Did all of this on my calculator, and I got 200. But what does that mean? It means on average, I have 200 cases of the tomato sauce in inventory at any time during the month. Let me ask, are you okay with this example? Okay with this example? Anybody questions? Are you okay with this example? I haven't tried it myself, but I would like to see if I can get my function integrator to do this for me on my TA84. Because again, I want to I want to have ways of checking my answers. Okay, I don't want to just get bogged down in the calculus somewhere and say, I don't know what to do next. I want to have a way of moving forward. Right? Are you okay if I try this on the TI-84? Try it on the TI? Okay, let's move over there and see how that works. I haven't tried it yet, so if it doesn't work, don't blame me. I didn't try it, but that's fine. Okay, I'm going to clear up some of this screen mess here. So I'm going to go into math, and I want function integrate. That's number 9. Okay, and again, remember, I need to know something about the problem in order to do this. Okay, so I'm going to put in my bounds, which are 0 to 30. Okay, and then I have my function, which was a kind of odd looking function. It was 600 minus, and then I had 20 times the square root of 30t. So 20 times the square root of 30t. And again, I can call it x, right? I mean, you know, it can be t, it can be x, it can be whatever. And then I'm integrating with respect to the same variable. Okay. Now, the only difference is I don't have my 1 minus 1 over b minus a. So I'm going to see if this will let me go back in front and insert in front of the integral sign. So I'm going to try that. Second insert, and it's not letting me do that. Okay, so what you have to remember is this still has to be multiplied by 1 over b minus a. Okay, so let's let this run. Okay, and it gave me 6,000. And then I'm going to take that and multiply that by what? Okay, that's 1 over 30 minus 0. So alpha y equals, here's 1 over b minus a. And there's the 200. Okay, so again, the advantage is you can use the function integrator on the TI to do these problems, particularly if they're going to let you round your answer. Okay, it's just you have to remember to multiply by this fraction, because again, the calculator won't let you insert in front of the integral sign. Okay, so just don't lose that piece. We okay with the TI example? All right, with how we did it? So again, that function integrate in the math menu is going to be a big help as long as you remember which integration formulas to use. Okay? And as long as you can approximate the answer. Okay, this one worked out easily because, again, your answer is a whole number. Okay, I'm going to stop sharing my screen with you for a minute and go back to the meeting. Okay. And I just want to ask, do you have any questions on anything? Anything we covered today? Any questions at all? Any questions? Because again, this is what we are here doing in chapter 16 is we're looking at applications of the definite integral. So we saw 2 of them today, namely solids of revolution, which again, don't have a huge business application. Average value, which does have a huge business application. And what we'll talk about next time is we're going to be talking about something that's really interesting called continuous money flow. And it'll kind of give you a way to compare investments today versus the value of them in the future. Okay, so that's what we're going to be talking about next time. So if you guys are all right, if you don't have any questions, you can feel free to drop off the conference at any point.